Okay, moving along. So I'm going to get into the next type of hybridization, which is sp2. Okay? And so as you might guess, sp2 hybridization can occur when we mix one s and only two p's. Okay? And so carbon can do this, nitrogen can do this. There's a lot of atoms out there that can do sp2 hybridization. And so what ends up happening in sp2 hybridization, we only use, let's see, we promote. So the first thing that happens is, this is missing the slide for promotion. Okay, so we promote this to make a 2s1, 2p3, all right? However, one p orbital gets left out of the mix, okay? So this is one extra atomic p orbital, okay? And so now what happens is what we should recognize, all right, let's see if I can do this with my Plato models here, all right? So now you might notice, well, why is there 5 things sticking out of there? Well, what we get when we have these 3 sp2 hybrid orbitals, okay, we should recognize that they are half filled, so there's only 1 electron in each of these sp2 orbitals, like that. There they are, 1, 2, 3. However, if you remember the shape of p orbitals, right, they have this like 2 lobes, right? Well, we'll have some extra electron. You know, it'll be either in the top one or the bottom one. Doesn't really matter. It's arbitrary. Okay. And we also get the 120-degree bond angle from this. And I'll go to my simulation here. Okay. And here I solved the equations for, or really I'm making my students do it. This is the answer key though. And so what you get, you notice this shape for sp2, the math predicts that it's 120 degrees. You have to take my word on it that this is 120 degrees. And the important part is that it's planar, right? Just like, let's see here. Now my Plato really does not hold up well. Okay, right? It's the trigonal planar, right? It is a plane, right? With 120-degree bond angles, okay? But now something really interesting can happen with these extra p orbitals, okay? And so what happens is we make a new type of bond, which is called a pi bond, or in other words, a double bond. So let's play with this molecule right here. This is called ethene. Okay? And ethene is 2 carbons with a double-double bond. All right? And if you notice here, if you look at each carbon is an sp2, or in other words, a trigonal planar arrangement. So it's 2 trigonal planars. So let's see if I can quickly build that with the Plato. Okay, so let's see. First, I'm just going to build the single bond. Oh man, the Plato is way too heavy for these toothpicks, right? So there are my 2 trigonal planars. I think my hands are getting in the way, right? Hopefully you can see that each one of those are trigonal planar, okay? But now, because if you look at this, this picture is getting crazy, right? So the overlap of the sp2 bonds makes the sigma. Okay, so I'll write sigma bond right here. Okay, so that means one of these bonds is what we call a sigma bond. And then now what happens is, hopefully my Plato holds up. These 2 sticks that are sticking up, right? So there's my trigonal planars, okay? But now these 2 sticks that are sticking up, those are the 2 available p orbitals, right? Okay? And when they overlap, when they become close to each other, like it's showing here, right? So far away, maybe they're they're not bonded, but as you get these things closer together, something like this, okay, it forms the pi bond, okay? So in this doubly bonded molecule, one of those bonds is a pi bond, the other is a sigma bond. And what's important to note, the sigma bond exists between the two nuclei. The sigma bond is what we call internuclear. The pi bond, I'll put another toothpick, the pi bond exists somewhere up here, okay? Off axis. So I'll say the sigma bond is internuclear. It's between the two nuclei. The pi bond is, I'll say, off axis, okay? And so let's see here. So before I go to this next example, I'll show you on my, on this simulation, this other one, how I can make a pi bond. And so this one is just showing you, because it gets rather complicated, it's only showing you how we make the pi bond from 2 p orbitals, okay? So here's 2 p orbitals, and I've got them about 2.05 angstrom apart. And so this space between the 2 p orbitals, where it says like, the 0.0, that's where the nuclei would be, okay? So the internuclear zone exists between here. That's what would create the sigma bond. But now watch what happens if I get these things really close to each other, okay? Thinking, computing, there's the pi bond, right? And we don't know really, we can't say with certainty if it exists on top or bottom. So you can see my model like calculates both, it predicts both. So this is not making, it's important to note, like this is not a double bond. There's only going to be an electron pair in either the top one or the bottom one, okay? But all the same, the nuclei exist between this region. And so if this were a model of an actually like double bonded molecule, we would just see a giant amount of electron density surrounding that internuclear zone, okay? And so that's actually what this picture shows right here. So let's look at the molecule formaldehyde. So that's this molecule right here. Formaldehyde, the stuff that, you store critters, the jars that have like the biological samples, bugs, and preserved things and the like, right? Formaldehyde. And if you notice the Lewis structure, right? The carbon, hydrogen, double bond, oxygen, that's making a trigonal planar, which I want you to recognize is sp2, all right? And so now you can see what happens here on this picture. Let me go back to my red pen. We've got a sigma bond here between the carbon and hydrogen, right? Sigma bond. We've got another sigma bond here between this carbon and hydrogen, right? We've got another sigma bond between the carbon and oxygen, okay, that exists between the two nuclei. And then now you notice the pi bond, it can be either top or bottom. I'll just draw it up there. There's my pi bond. So 3 sigma bonds and 1 pi bond. And you also notice that if you look at oxygen here, the oxygen hybridization, it's also sp2 hybridized. However, because it has these 2 pairs from the atomic configuration, this predicts the 2 lone pairs on oxygen. So this is all good. This really matches up with all of the theories nicely, okay?